Hey everybody, we're going to be going over Chapter 2 PowerPoint presentation focusing on hydronic heating and cooling principles, mainly on what human comfort is, principles of heat transfer, how temperature, humidity, and pressure relate to it, and the calculations involved in it. In this chapter, we'll be discussing how heat transfer affects human comfort, explain what heat transfer is. We'll be defining radiation and explain how it functions within hydronic systems, compare conduction and convection, define evaporation, and explain how it functions with hydronic systems, discuss the intensity and quantity of heat in a hydronic system. We will also explain how heat causes changes of state, define enthalpy, discuss humidity and how to control it, discuss different types of thermometers, discuss different types of pressure in a hydronic system, explain how head pressure and static pressure are related to pressure drop, list the factors in selecting a pump or circulator, and discuss water flow rates and water flow velocity. We will start beginning with how heat transfer affects human comfort. So, the main purpose of any type of heating or cooling system is to provide comfort to an individual within a building. Comfort is that condition in which the human body feels neither warm nor cold and it's at thermal equilibrium with the ambient temperature. Comfort is not achieved by supplying heat to the body. Comfort is achieved by controlling the rate and manner in which heat is transferred from the body. This is accomplished by controlling the temperature of the air so it remains within the narrow range of temperatures within which the human body is comfortable. As the ambient temperature rises or falls, the body will attempt to regulate itself through bodily functions. Externally, body heat loss or gain will be affected by the principles of heat transfer: radiation, conduction, convection, and evaporation. For comfort conditions to occur within a building, hydronic heating and cooling system must assist in keeping body heat loss within the correct proportions of heat transfer. So heat transfer is the flow of heat from one object or substance to another. It occurs because of the difference in temperature. For example, because the difference between the temperature of a person's clothing or exposed skin and that of the air, heat flow from the warmer object or substance to the cooler one. There are two general ways in which the human body transfers heat to its surroundings. These are by dry heat exchanges involving sensible heat and evaporated heat loss involving latent heat. Dry heat exchanges involves radiation, conduction, and convection. Evaporative heat loss occurs through bodily perspiration and its evaporation. Radiation is the exchange of thermal radiation energy between two or more objects. Radiation does not require a medium between the two objects for heat transfer to take place, as opposed to conduction or convection, which do require a medium to transfer heat. Heat is transferred through space to objects in the path of thermal radiation energy waves. Whether the radiation result in the body gaining or losing heat, the rate at which the gain or loss occurs depends on the difference between the temperature of the body surfaces or bare skin and clothing and overall average of the temperature of the surroundings. The overall average temperature of surrounding surfaces is called the mean radiant temperature. Radiation heat transferred to or from thermal units is used to heat or cool the air, the building components, and the occupants in the building spaces in a way similar to the way the sun heats the body. Terminal units such as radiators, baseboard radiators, radiant heat panels, and radiant floor systems use the principle of radiant heat transfer to heat or cool building spaces in an appropriate temperature. Conduction or thermal conduction is the flow of heat through an object or substance, or the flow of heat from one object or body to another when the object or body are in direct physical contact. The transfer of heat is a direct result from the difference in temperature between substances. The rate of heat transferred between two regions is proportional to the temperature difference between them and the heat conductivity of the substance. The hydronic system uses the principle of conduction in the generation of the hot or cold heat transfer fluid that will flow through the piping system to the thermal units. Convection is the transfer of heat in which heat is removed from one location to another through a circulation of fluid such as air or water. There are two types of convection: natural convection and forced convection. Natural convection occurs because of a combination of heat transfer by conduction and heat transfer by actual movement of some of the fluid from one place to another. The use of fans and blowers to assist heat transfer by convection is called forced convection. Convection occurs when the heated heat transfer fluid within a boiler or storage tank rises to the top of the tank and cooler fluid descends to the bottom to be reheated. Evaporation occurs when perspiration changes state from liquid to a vapor. This evaporative heat loss allows the body to regulate itself to a proper temperature when the other methods of body heat loss are not enough to keep the body cool. The rate at which the evaporation and removal of body heat occurs depends on the humidity of the surrounding air and its velocity over the skin surfaces. Evaporation and evaporative heat loss occur in a hydronic cooling system when the refrigerants are used in chillers such as heat transfer medium to cool heat transfer fluids. A refrigerant is the necessary working fluid inside a chiller that will evaporate or condense at specific temperatures based on operating pressures of the chiller. Heat is a form of energy associated with the motion of atoms or molecules in a substance. Heat that causes changes in temperature that can be measured in sensible heat. The amount of heat in a British thermal unit requires the change of temperature of 1 pound of a substance 1 degree Fahrenheit is called the specific heat of that substance. Temperature is an indirect measure of the velocity attained by the molecules in a substance and is a measure of the intensity of heat. The amount of increase or decrease in the temperature of a substance depends upon the amount of heat produced or removed. Although temperature indicates the intensity of heat, it does not in any way indicate the quantity of heat. A practical measure of heat is the quantity of heat needed to raise the temperature of a given weight of a substance. The basic unit used to measure the quantity of heat is the British thermal unit. For practice purposes, 1 BTU is the amount of heat needed to raise the temperature of 1 pound of water by 1 degree Fahrenheit. Another unit of heat is the kilojoule, which is used in the metric system. For practical purposes, 1 kilojoule is the amount of heat needed to raise the temperature of 1 kilogram of water by 1 degree Celsius. By comparison, 1.055 kilojoules represents the same amount of heat as 1 BTU. We will now explain how heat causes changes of state. Upon absorbing a sufficient quantity of heat, the solid will melt and change to a liquid. The temperature at which this occurs is called the melting point. When heat is added to the liquid, the temperature of the liquid will rise. Upon absorption of a sufficient heat, the liquid will change to a gas or vapor. For any given substance, the temperature at which this occurs is called the boiling point. Depends on the pressure being exerted on the substance. The higher the pressure, the higher the boiling point. Then, upon further addition of heat, the temperature of the vapor will rise. When the vapor is heated to a temperature higher than its boiling point, it is said to be superheated. The process is reversible. Beginning with a superheated vapor, heat removal will first desuperheat the vapor until its temperature drops to the boiling point of the substance, at which point it is saturated. The change that occurs when a substance changes from solid to liquid, from a liquid to a vapor, or vice versa, is known as change of state. On this chart, you can see how pressure and temperature affects the boiling point of water. As you can see, where the gauge pressure is 0, or it's at atmospheric pressure, your boiling point of water is at 212 degrees Fahrenheit. As you see, when you put it into a vacuum with the numbers above, the boiling point starts decreasing. And inversely, as you see, when you start adding pressure, the boiling point rises. Now we are going to also define enthalpy. Enthalpy is a property of a substance that is measure of the energy it contains expressed as heat. Enthalpy is a way of expressing the total energy possessed by the molecules of a substance. Although a strictly proper definition of enthalpy involves some highly mathematical terms, for practical purposes, enthalpy may be taken as the sum of sensible heat and latent heat. The term enthalpy is used in connection with air, steam, or water vapor and refrigerants. The enthalpy of a substance varies according to the temperature of the substance, since temperature is a measure of the intensity of the heat and the energy possessed by the substance. Let's now discuss humidity and how we may be able to control it. Humidity is the amount of moisture or water vapor in the air. Humidity is always present in air. A low humidity level indicates dry air that contains little moisture. A high humidity level indicates damp air that contains a significant amount of moisture. When the air has absorbed all the water it possibly can at a given temperature, it is called saturated air. Another term for saturated air is 100% humidity. Relative humidity is the amount of moisture in the air compared to the amount of moisture the air would hold at the same temperature when the air is saturated. Relative humidity is always expressed as a percentage. Dry bulb temperature is the temperature of air as taken with standard thermometer. As long as the bulb or other temperature sensitive parts of the thermometer is kept dry, the reading of the thermometer is not affected in any way by the humidity in the air. Wet bulb temperature is the temperature of air as if it were cooled to 100% relative humidity. Wet bulb thermometers at a given dry bulb temperature is directly related to humidity. As you can see on this chart, how it illustrates how various dry bulb and wet bulb temperatures affect relative humidity. Humidity control is normally not a function of a hydronic heating system. When heating, it may be desirable to add moisture or to humidify the air to prevent the moisture content from being too low. This can be done with a separate humidifier. In cooling conditions, one of the functions of the cooling system is to reduce indoor humidity until a feeling of comfort is established. This is called a psychrometric chart, on which the comfort zone is indicated in the yellow shaded area. This chart takes account of a dry bulb temperature, humidity ratio, the relative humidity, and the enthalpy of a given situation. A psychrometric chart can be used to determine relative humidity. Instruments for measuring and indicating or recording relative humidity are called hygrometers. Some hygrometers give a direct indication of relative humidity and may indicate dry bulb and or wet bulb temperatures. Sling psychrometers typically indicate dry bulb and wet bulb temperatures, and, when properly used, the relative humidity can be determined by referring to a table or chart. This is an example of a chart table where you can use the dry bulb and wet bulb temperatures to determine the relative humidity. Discussing the different types of thermometers. A thermometer is any instrument used to measure temperature. Thermometers used to measure air and liquid temperatures are typically manufactured in one of four types: liquid and glass, dial, thermistors, and infrared. The two scales commonly used on thermometers in North America are the Fahrenheit scale in the United States and the Celsius scale in Canada. A liquid in glass thermometer, also called a glass stem thermometer, is commonly referred to simply as a thermometer, without specifying any particular type of thermometer. Operations of this type of thermometer is based on the principle that materials expand when heated and contract when cooled. A dial thermometer is an instrument designed to measure temperature using a circular scale and pointer. Dial thermometers are two general types: a stem type and the flexible capillary type. Their advantages are that they are more rugged and more easily read than glass stem thermometers, and they are fairly inexpensive. A thermistor is a type of resistor made of material whose electrical resistance varies with temperature. For use as a thermometer, the thermistor is placed within a sensor or probe that is connected to an electrical circuit containing a sensitive electrical meter, a battery, and a number of resistors. Infrared thermometers are thermometers that measure temperature by detecting infrared energy emitted by a substance that have a temperature above absolute zero, or negative 460 degrees Fahrenheit. The infrared thermometer may be used to measure the exterior temperature of a thermal unit, the temperature of a pipe, or the discharge air temperature of a ceiling diffuser. This saves the time required to move and use ladders. Pressure is a force per unit of area, or pressure is equal to the force divided by area. Pressure, according to the height of a liquid, is called head. At any point below the surface of the water that is exposed to atmospheric pressure, the pressure is produced by the weight of the water above that point. This pressure is variously called static head, static pressure, hydrostatic head, or hydrostatic pressure. Static head is expressed in units of length. For example, both 0.433 psi and 62.4 pounds per square foot are equal to 1 foot of head. Atmospheric pressure is the force exerted by the weight of the atmosphere on the Earth's surface. The standard pressure, due to the weight of air at sea level, is 14.69 pounds per square inch, or pounds per square inch absolute. This is usually rounded to 14.7 psi. Gauge pressure is a pressure measurement above atmospheric pressure that is used to express the pressure derived from the operations of a closed system. Since gauge pressure does not include atmospheric pressure, 0 psig is equal to 14.7 psia. Absolute pressure is any pressure above a perfect vacuum, 0 psia. Absolute pressure is the sum of gauge pressure plus atmospheric pressure and is a measure in pounds per square inch absolute, or psia. Vacuum is any pressure that is less than atmospheric pressure. Vacuum is not measured on a standard psi scale. Vacuum can be measured in units of inches of mercury. Pressure drop is a term used to describe power that is consumed in moving liquids through pipes, terminal units, fittings, and other system components. Expressed another way, pressure drop is the amount of pressure lost between any 2 points in the system. Pressure drop in a pipeline is caused by the friction created between the inner walls of the pipe and fittings and the liquid flowing through them. Enough power must be available to overcome the effects of pressure drop before a system will operate. In a hydronic system, this power is provided by the pump or circulator. Manufacturers that publish pressure drop information on their equipment express the data in pounds per square inch, in feet of water, or in millinches. Head pressure, as used in designating the capacity of a pump or circulator, is merely another way of expressing pressure drop. The maximum head of a pump, usually expressed in feet of water, is actually the maximum pressure drop against which the pump can induce a flow of liquid. Head pressure and pressure drop should not be confused with static pressure, as they have no relationship. Static pressure is created by the weight of water in a system and is equal to 0.433 psi of height above the gauge. Static pressure is in a closed system has no effect on pump capacity. Factors in selecting a pump or circulator: the number of gallons per minute required to carry the heating load must be found in order to determine the size of the pump and piping. To determine this number, the temperature difference between the inlet and outlet water of the heating units must be known. For a 20° Fahrenheit drop, the gallons per minute are found by dividing the heat load by 10,000. A hydronic heating or cooling pump or circulator is selected on its ability to move a specified quantity of water at a specific resistance. When discussing water flow rate and water flow velocity, the amount of heat transfer depends on many things, but two important factors are the flow rate and the water flow velocity. Water flow rate is the volumetric flow rate of water as it moves through a given pipe section. A water flow rate needs in hydronic systems are based on the temperature difference of the water at 2 points in the system and the amount of heat transferred during the change of temperature. Water flow velocity is the speed of water moves through the piping section, typically expressed in feet per second. Water flow velocity in hydronic systems is based on the water flow rate between 2 points in the system and the size of piping.